Hi guys, David here with another science update. So today we're going to talk about new research that opens the door to a possible new generation of face masks that could actually kill the COVID-19 virus, various bacteria, and maybe even inactivate chemical weapons agents. So let's start off by looking at this article that came out this week. It's called "A Rare Feat: Material Protects Against Both Biological and Chemical Threats." The article says, a Northwestern University research team has developed a versatile composite fabric that can deactivate both biological threats, such as the novel coronavirus that causes COVID-19, and chemical threats, such as those used in chemical warfare. A material that is effective against both classes of threats is rare. The material also is reusable. It can be restored to its original state after the fabric has been exposed to threats by a simple bleach treatment. The promising fabric could be used in face masks and other protective clothing. One of the lead scientists says, having a bifunctional material that has the ability to deactivate both chemical and biological toxic agents is crucial since the complexity to integrate multiple materials to do the job is high. And it says that the basis of the technology is something called metal organic frameworks, or MOFs. So a metal organic framework is a class of compounds consisting of metal ions or clusters coordinated to organic ligands to form 1, 2, or 3-dimensional structures. So basically the idea behind a metal organic framework is that it's a combination of metal ions and then organic compounds that form sort of these bridges or spacers. And so for instance, you can see in this image that you have these ZN, that's zinc. Zinc is a metal, and you can tell that it's coordinated with oxygen, so it's zinc oxide. But then these black lines signify bonds, basically covalent bonds, and then covalent bonds to carbon-containing compounds or organic compounds. And so the idea behind a metal organic framework is it's sort of a combination of these metal structures where you have bridgers, or what are called sometimes struts, that are organic compounds that basically space the metal clusters out from one another. And then you wind up with this kind of cool combination of it's kind of like a metal. It has some properties of metals, like for instance the ability of metal to coordinate certain other chemicals, but it also has more of the flexibility and structural characteristics of like a plastic, for instance, depending on the composition. An example of a bridge molecule, this might be the strut or the organic portion. One common one is terephthalic acid that you can see here. So all of the black lines signify basically carbon-carbon bonds. So you have a 6-membered carbon ring, a benzene ring, and then it has 2 acid groups coming off of it. This is a carboxylic acid group on this end and a carboxylic acid group on this end. And basically what these acid groups can do is they can kind of coordinate, which is to say form like a relationship with a metal ion. And if you think about it, if you have a bunch of metal ions and you have a bunch of bridges, it basically forms out this 3-dimensional lattice structure. And depending on a lot of factors, including things like the choice of the organic bridge molecule, the choice of the metal you're using, and the ratio between the two, you can actually build out sort of different geometric patterns that might, for instance, have different pore sizes. So you can see here, this is a different paper where you see how 3 different arrangements actually cause 3 different pore sizes. You can see the pores, like would be the empty spaces in between, and depending on how these structures are put together, you have kind of like very small pores to very big pores. And a factor like that is going to influence things like the performance and what they can be used for. So back to our first article, it says that MOFs are sophisticated bath sponges. The nano-sized materials are designed with lots of holes that can capture gases, vapors, and other agents the way a sponge captures water. In the new composite fabric, the cavities of the MOFs have catalysts that can deactivate toxic chemicals, viruses, and bacteria. And also this porous nanomaterial then can be easily coated on textile fibers. So the idea is the metal organic framework can actually be incorporated and coated onto the type of fiber that you might use to weave a face mask. The researchers found that the MOF fiber composite exhibited rapid activity against SARS-CoV-2 and both gram-negative bacteria like E. coli and gram-positive bacteria like S. aureus. Also, the active chlorine-loaded MOF fiber composite rapidly degraded sulfur mustard gas in its chemical simulant. Meanwhile, the nanopores of the MOF material coated on the textile are wide enough to allow sweat and water to escape. And so that's key, right? We were talking about that idea of porosity. Depending on how you build out your metal organic framework, you'll be able to have large pores or small pores. And I guess that they designed this one with large enough pores that water molecules and sweat and whatnot could actually get through. So looking at the specifics of the metal organic framework they used, it looks like they call it a zirconium metal organic framework, which also has amine groups, so UIO66NH2, which they then use to incorporate chlorine as one of the main active disinfectants. So you can see here in their image, they have this metal organic framework material, and they're zooming into one portion. You can see the green, I believe, represents the zirconium, and you can see those familiar black lines, those little struts or structures, and you also see these little light blue dots are signifying chlorine molecules. It looks like the chlorine is the active ingredient for most of the biocidal component. So they say a chlorine bleaching converted the amine groups located on the MOF linker to activate N-chlorine structures. And so it's actually, the chlorine looks like it's actually coordinating with the NH2 groups on the linker. The fibrous composite exhibited rapid biocidal activity against different types of bacteria, as well as the SARS-CoV-2 virus. Then it said, moreover, the active chlorine-loaded MOF fiber composite selectively and rapidly degraded sulfur mustard, which is a chemical weapons agent, and its chemical simulant 2-chloroethyl ethyl sulfide, or CES, with half-lives less than 3 minutes. One thing that's unclear to me from this description is if it's just the chlorine that's doing the degradation of the sulfur mustard and killing the bacteria, or if the zirconium component of the metal organic framework has some role. So that's something I'd like to understand a little bit better. And they say the versatile MOF-based fibrous composite designed here has the potential to serve as protective cloth against both biological and chemical threats. So I don't really like the idea of having to need such a mask. You know, if like there was, not only do we have COVID-19 going on, but also if the threat of a chemical weapons attack was imminent, that would be pretty nerve-wracking. But it does happen from time to time. Sometimes people do get mustard gassed, and so I guess it would be nice to have this mask if that's the case. It looks like this is pretty early on research right now, so I don't think that this is going to be rolled out in face masks anytime soon. But hopefully they can look into scaling it up. They do say the composite material is scalable, as it only requires basic textile processing equipment currently used by industry. And they say when incorporated into the face mask, the material should be able to work both ways, protecting the mask wearer from virus in his or her vicinity, as well as protecting individuals who come into contact with an infected person wearing the mask. Right? That's a good point. If you're contagious for COVID-19, for instance, and you're breathing out virus through the mask, if the mask is actually killing the virus as well as just filtering it out to some extent, to some limited extent, then that could really improve the efficacy. Anyway, this has been another science update. I hope you'll join me again soon, and if you enjoyed the video, please like and subscribe, and join me again in the future soon. Bye.